Alright. This is a sort of, in a way, continuation of introducing what we call acid-base equilibrium. Okay, so I'm going to pop around the notes a lot, and I think if I remember correctly, I reorganized the notes that you do have, so they may not have the exact same page numbers as we go through. So you're going to have to look at the format of the page, find the appropriate page. I don't think I brought home my current set of notes to look at. Oh, good, I did. So before I get into the notes, because I want you to pay attention to certain things as you take notes. So I'm going to go over what's really important in acid-base equilibrium. So things you need to pay attention to, things that as I go through them, you want to make sure you can go back and process it and come up with a way that you can recall how to do the thing, because it's really important. So what's important? Ooh. What will be the take home that you absolutely need when you talk about acid-base chemistry and this acid-base equilibrium? Now, the important concept is that it is an equilibrium. No more, no less. It is equilibrium. We are going to look at disturbances in response to acids and bases in equilibrium. You know, which way does it shift? Okay, so just because it is a specific subset, don't let that phase you. It's equilibrium. Which way does it shift? What side goes up? What side goes down? If we want it to make it go a particular way, how can we do that? That is titration, essentially. That is common ion. That is solubility and precipitation. That's a little separate thing. That's what we do at the end of this unit, which is, in addition, it's more equilibrium. It's not really acid-base equilibrium. So when we look at this equilibrium, there are a few things that are utmost important. One thing you have to do is know how to make a buffer. And I'm going to say how to choose a buffer system. And we'll go over that. Know how to make a buffer based on that choice. So as you take notes, these beginning notes, we're focusing on some of this top part. There's two ways. You need to know when to use each way. And it's not that hard. If you like to memorize stuff, this is going to be like your bag here, because it is a memorization thing. Okay, then you need to be able to calculate the pH of a buffer. Now, they don't make you calculate the change in pH, but you need to be able to explain how the pH will change if something's added. How a buffer works. Okay. And in a way, why is that doing that? In a way, guys, I'm going to try to sharpen my little pen here, see if it works and doesn't glitch on me. You also need to know, as a subset, how an indicator works, because that actually is an equilibrium. It's equilibrium, so don't forget that. Okay. Get that off of there. Alrighty. And when we look at this, essentially for this acid-base equilibrium, the next thing you're going to do is be able to calculate pH along a titration curve. Again, this is all equilibrium. Okay? So as we progress through this packet of notes and the concepts we practice, keep these things in mind, that this is what, you need to know these things and be able to pull this out and use it. So I'm going to go back to the notes. I was just scrolling through to see where we left off. Okay, so the other day, Friday, we started talking about this common ion thing. We started talking about how it is an equilibrium here. We've got the equilibrium of our acid going on. We add in a common ion, it shifts. Okay, and we're going to say the thing that we're missing is our X, and we're going to use the K values to figure out the missing X. Sometimes that missing X will be the OH minus, sometimes it'll be the H plus, but that is common ion, and we're going to revisit, in a way, common ion throughout this and later on. But now I want to get to buffers. Now, buffers are extremely, extremely important in a biological system. I'll do it this way. I don't want to launch this like in a PowerPoint type of thing because for whatever reason my stylus with that type of a program ends up making these random straight lines all the way across the notes. So I'll have to keep coming in and out of the write-on function in the computer. All right, so again, I can't stress enough, very important in biological. You look at buffers to maintain the homeostasis for the system you want. Okay, now, this is really important. When you look at buffers, every buffer has something that's a weak acid or base. Okay, weak. That is the principle behind it. It is weak. You cannot use anything strong. Weak because you have equilibrium with the weak. That's how a buffer works. Okay, strong is not acceptable. So this is why you need to know your strongs, because it won't work with a strong. There is no equilibrium. So you have to always look, when you go to create a buffer system or evaluate a buffer system, if they ask you, will this buffer be a good buffer? You must make sure it is made from a weak acid or a weak base and its counter ion, right? It's conjugate base, it's conjugate acid. Okay, so it has to be from the weak with its counter ion. So this is why I decided to take a little extra time with acid and base and make sure this is that whole thing of, we have HA and its A minus. We have B with its BH plus. Okay, weak. So now, there's essentially two ways to make a buffer. We have to have both things present in order to have a buffer set up. Right, we need both things present. Let's see if I can do this. All right. Now, I just switched back to the notes. Let's go back up here when we did this common ion, right? When we did this common ion, we had the acid, and we added in as a common ion its conjugate base, and we have two things present because I took a salt and added this in. So technically, down here where I had the acid and the sodium acetate, I have a buffer now. And literally, this is what we call an ideal buffer. Exactly equal acid to the conjugate. Down here I have a buffer, but it's not ideal because this is not equal to that. So all of these common ion problems about, oh, we have a new pH because we now throw in a salt of the weak acid, every single one of these is, believe it or not, a buffer problem. So you've already done buffer problems. You just didn't know. So now I gotta see if I can find where this went. Hold on. There we are. So in your notes, and I believe this is page 3. Yeah. There's 2 ways to make a buffer, right? And the 2 ways are this. And this is actually going to sum it up really short. So it's like bullet point. Here's the first way, here's the second way. So the first way is if they tell you you only have the acid and you have a base off the shelf. So you got a weak acid and you got a base. Now, in order to get a buffer, you need to have the acid with its conjugate ion, right? To get a buffer, I've got HA, but I don't have the A minus. So if I neutralize it, that gives me the A minus. By neutralizing, I make this A minus and I throw it back in the original and I remix it, and then I have the 2 of them present. I have this present with that. Okay, so that's number 1. That's the first way. You can do the same thing with the base. If they say you have a base and you go into the stockroom and you pull an acid off the shelf, you neutralize it to make the counter ion. So if I want to make my little base, I have my base, but I need the BH plus. So neutralizing gives the BH plus. And now I have the both of these present going back and forth. So I've made the buffer by neutralizing, right? And I'm going to just do this little dash across the line because these are 2 separate methods to make buffers, right? The second method, which is listed as number 2, is that you're going to take, you're allowed to go into a stock room and take what you want. And a lot of times they list a ton of chemicals. They say you go into your stock room and you have all these chemicals. Choose the 2 chemicals to make a buffer and describe the procedure. And you need this buffer to be a certain pH. So when you do that, if you have all of these chemicals to take, you look for the weak acid and the salt of the weak acid, and you measure them and add them in equal amounts. Okay? Equal number of moles in the same volume. Okay, equal number of moles in the same volume. That gives ideal buffers. Oops. I want to say same volume, and because I said the word buffer, I stated it. Same volume. Right? If you have equal number of moles, of the acid in the conjugate, or base in the conjugate, oops, that equals an ideal buffer. And you might say, why do they call it ideal? Because it's the best scenario for making the greatest buffering capacity. Okay, it buffers the best, so they call it ideal. You can have different ratios and it just won't buffer as well. It'll still buffer, but it won't be optimal. Okay, so ideal really just means that you're optimal. It's the best case scenario. Okay, if they tell you you need a buffer that's a basic pH, you want a buffer at a pH of 10 because your cells like pH of 10. Then you're going to be on the base side and you'd have to go get a weak base and its salt. And I am going to tell you right now that the ones they love are these: ammonia and ammonium chloride. Because in technicality, remember when you throw the ammonia into the water, you make ammonium hydroxide. That's AP's favorite scenario. They can use different kinds of salts here. They can do the methyl ammonium chloride, the ethyl ammonium chloride, the dimethyl ammonium chloride. Okay, but it's an ammonium chloride. And whenever you see ammonium chloride, you're going to think, oh, I'm using ammonia as the base. Okay, I'm going to close and reopen this because I want to shift the notes for you. So let's shift down. All right, now we have to adjust something because I made a typo in your note. I don't know how I picked the wrong page 3 and put it in your note packet. Okay, because I had it like this and it was fixed, and your note packet has it wrong. So I had to, like I said, when we were going through it, I'm like, what the heck? I've got all these typos. I thought I fixed it, and I must have picked like an old version of it in the file to send out to you. All right, now if we look at the very top, to choose the right buffer system, we have to look at the Ka and the exponent of the Ka. And the exponent of the Ka is really, oh, I wish this wouldn't do that, is really your pKa, right? If you have negative, remember, pKa is equal to negative the log of the Ka. That'll focus on the exponent. So you really, pKa focuses on the exponent because you're doing the log of. So if I tell you I want a pH near 5, most of the time you use acetic acid because 1.8 times 10 to the minus 5 is the Ka. And then if you take negative the log of that, you're going to get a pH that's close to 5. It's actually 4.74. Okay, and so acetic acid and its conjugate, like sodium acetate, would be the system for a pH of 5. I want a pH up near 9. It's your weak base of ammonia and ammonium chloride because the Kb is 1.8 times 10 to the minus 5. So if you flip that into a Ka, right, and it's based on Ka, right? So this is why over here, if you notice, look at the exponential value of a Ka. So you have to be careful. You've got to take that Kb they give you and change it into the Ka. So you have to think what adds up to 14. So if I had 10 to the minus 5 as my Kb, then my Ka is going to be 10 to the minus 9 for the Ka. So I will be pH around 9 in a base. Remember that. They love to mix the two together and see if you get caught not realizing you're looking at a Kb. Alrighty. Now, when we actually go to calculate buffer problems, there's 2 ways to solve them. One is to do the rice, which that's page 1 and 2. So if you're like, I love rice, I don't want to learn something else, here's the thing, and I talked about this in class. If you decide you love to do rice, you have to do the molarity. You need concentration. You have to have concentration, which means when you look at that, and let me change this little, you have to make sure, on a different one, that you are looking at total volume and concentration. They'll always say you mix so many milliliters of this and so many milliliters of that. So you have to make sure that if you are going to do ice or rice, you better have concentration. My favorite is the Henderson-Hasselbalch. Okay, and I just call it HH. Henderson-Hasselbalch's my favorite. All right, now it is on the rough table for this. This version is on the rough table. Your base is not on the rough table, so you have to either memorize this or be able to come up with it. Now, I have had some very crafty and alert students who can take this top one right here and actually, when they work with the base, still plug this in, because they change the KB to the KA, and then they make sure that they do this inverted ratio here. They put the base on the top and the BH plus on the bottom, and it works. But you have to be able to keep that straight. So it depends on how alert you are and how good at your mental processes for keeping it straight. A lot of times it's not that hard to get these down. Now, please note, please note, look at these. This is where the typos are in your notes. Like I said, guys, I don't know how I ended up picking that. I thought I threw all of those away. So remember, this is POH, PKB, okay? POH, PKB, I think yours says pH and PKA. That's bad. Okay, so this is the base. When it's base, if you're going to use the HH towards base and not convert it into the KA, because you can go back and forth, make sure you make that change in your notes. Right? Now, this is Miss Silvestri's favorite way of doing it. I know this says concentration, but in actuality, you only need number of moles. And there is a particular way you figure out the moles of each. All right, so just keep that in mind. I will show you both ways. When we go to do homework, I'll say, okay, this is by Henderson-Hasselbalch if you chose that method. Oh, now I'm going to show you if you chose the Rice method. You have to decide what works for you. Both are valid. Both are. You just have to make sure you're using them the right way. That's kind of the nice part about this. You get to work with your own brain and say, oh, my brain works this way. I'm going to use Rice. It works that way. And I'm going to say, that's great. You can use Rice. I will say to you, though, for me, time-wise, I'm much faster solving with the Henderson-Hasselbalch. Okay, that doesn't mean you will be. And that's why you get to choose what works for you. And this is one of those things where, hopefully by now you're kind of used to the thought, I can decide which way to do the problem for my brain's wiring. I'm not going to say to you, you have to do it this way. Because you don't. There's more than one way to do it. Hence the reason why I always say to you guys, can't stand what they teach you in elementary school. Because it's so bogus. Okay. Let's do some of these problems. I'm going to go through them two ways. I'm just going to do the first one, and then I'm going to ask you to try to do them and then check with the notes. So I'm going to go through the first one. I'm going to use the whiteboard, and we'll go through the first one. So I'm going to erase everything that's on here. I got to get the problem out, though. So number 1 on page 4 says, we have lactic acid. Come on, where'd my whiteboard go? Wow. And lactic acid. And guys, you know what? I'm going to be lazy. Why does it keep doing this to me? I'm going to be lazy. I'm just going to call lactic acid HA. Can you write out the lactate? Yes. If you look at the notes, I've written out the lactate. And lactic acid has an equilibrium when you put it in water. Now, I want to figure out the pH of the solution where I have 0.75 molar of this and I have 0.25 molar of this, and they give me a Ka. And where is my volume? Actually, I really don't need the volume because they gave you the molarity of each thing. And it says my lactic acid is 1.4 times 10 to the minus 4th. All right. Now, 2 ways to do it. Let's do rice. Remember, rice, you have H plus times A minus over HA is going to equal your Ka, which we have as 1.4 times 10 to the minus fourth. I'm going to plug in. We don't know H. Oh, if we find H, we can find pH. We have this. Now here, it's very nice. This one's a nice, easy problem in the sense they gave you the molarity of everything. But if they say you mix 30 milliliters of the acid at 2 molar with 40 milliliters of the conjugate ion at 2 molar, right? They're not both 2 molar after you mix them because you mix 30 milliliters with 40 milliliters. Now you have a different volume, so you have to calculate your new concentration. So just make a note, read it carefully. If mixing two different volumes, mixing solutions, you have to calculate the new concentration because their concentration will change. Okay, so I solved this. Well, the concentration of H plus, you plug in your calculator and solve, is 4.2 times 10 to the minus 4. So if I do the pH of this, which is negative the log, just like we've been doing, no different than before, other than, oh, we're starting with, so the only difference, guys, is that you're starting with this, right? Like a common ion. So my pH is 3.38. So this is method number 1, rice. Method number 2 is Henderson-Hasselbalch. Now, again, this is a straightforward, easy one. So, and I'll show you what I mean. pH is equal to pKa, negative the log of that, plus the log of the concentration of the A minus over the concentration of the 8A. Now, this right here. Okay, if you mix volumes, we're not on this problem. Find moles of each and plug in. You don't have to calculate the new concentrations, just the number of moles you took of each, right? And number of moles is going to be liters times molarity will give you the number of moles of each. Just keep that in mind. So my pH is going to be equal to negative the log of 1.4 times 10 to the minus fourth. And I apologize, I'm writing on an angle, guys, so my handwriting is not all that great when I do this. And then again, because we're not mixing volumes, I'm just going to take the concentrations right from the problem. But if you were to do this, you'd get 3.85 minus 0.48, and that's going to equal 3.38. Oh, look. This and that are the same, two different ways. Okay? What is a buffer? A buffer is this. This part is what we talk about buffering. That ratio between A minus and HA is the buffering that goes on. All right? If you're equal in mounts here, if A minus equals HA, you have the log of 1, which is 0. Okay? And that is ideal. You equal the pKa. All right. Now, what I want you guys to do is to try the other problems up through page 5 and then go back and check on it. And I'm going to briefly go through buffer capacity. And then on Monday, we're going to talk more about buffer capacity and calculating things. So buffer capacity literally is how well can a buffer hold the pH at a particular level when you add stuff into the solution, an acid or a base into the solution, right? So what happens when you look at buffer capacity, and I'm going to move this up just a little, so we have our little pictures, although I may have to redo this. Whenever you look at buffer capacity, what you're really looking at is this ratio. Okay? How much this value changes, because this is your starting point, so to speak. And a buffer works by going back and forth in your equilibrium. And guys, so do indicators, because indicators, the reason why they change color is their equilibrium shifts. And you go from something, let's say, like phenolphthalein would be colorless at one pH, and then it's purple or pink at the other pH, and it's this back and forth. Essentially, you're in this roundabout thing where you make this, and then this goes back to this. So if I add in an acid, if I add acid, I react with the A minus and make more HA. If I add a base, okay, so if I add a base, let me change my color. Right? If I add a base, I react with this, right? And I essentially, right, if I add a base, see, I have to think this out myself. Yeah, a base like an OH minus, right? The OH minus is going to react with the H plus, and you shift the equilibrium. If you add in an acid, you go back the other way. So the base takes this out, the acid adds that in. And so, you have this, I either go back this way or I go this way. And it's how how the system responds and how much it shifts, and it changes this ratio. Okay, that's how a buffer works. The buffer is based on this ratio. Right? So keep that in mind. That's how a buffer works. It's based on that ratio. I'm going to move this up a little. Alrighty. If we set up our buffer so it's not ideal, and we have more acid in the buffer than we do conjugate base, and we go to calculate our pH will end up less than the pKa, because you're going to end up minusing a value from that pKa. Right? So if I add acid into this, I'm not going to have much capacity to buffer it. I don't have much of this. If I add base, I can buffer it for a while. If I go to this other side over here, where on the opposite end, I have a buffer that has way more of the conjugate base, very little of the acid. So the starting pH of that, right, so now this ratio of A minus over HA is greater than 1. So we're going to add to the pKa when we do that negative log. Right? So your pH becomes greater than your pKa. So if you add acid, you can buffer, because you got all these A minuses to interact with it and give you a nice range of buffering. But if you add base, there's very little HA there to buffer it. This is the ideal buffer, because you're in equal ratios. You can add base, and you got some HA there to make more A minus. You can add A minus, H plus, and you have A minus to interact with it. So you have a range that's going to give you a better buffering situation. All right. Now, this is really important, is that the higher amounts you have of both of them, right, the more concentration of your acid in its conjugate base, or its base in its conjugate acid, you can do it for a base buffer, the better it buffers. Okay, the more stuff can be added in, and the more it can interact with it and reestablish the equilibrium. So you always strive for ideal, and that is by having equal moles of acid in the conjugate base or equal moles of base in the conjugate acid. All right. So here, if they tell you you want a 100 milliliter solution of a 0.5 situation concentration of your buffer, then you want to make sure that you have the right amount of moles, because you're going in 100 milliliters here. So you want 0.05 moles, right? 0.1 times 0.5 gives you 0.05 of both the base and the acid. And so, you can either measure out how much base you need and add it to the volume of the acid, or remember, you can take half the volume of the acid, neutralize it, and pour the two back together. All right? So keep that in mind. And the other thing is, once you make a buffer, if you dilute it, the pH, the starting pH is the same. They always try to trick you with that question, because your ratio of your ions don't change. Right? Think about it. This ratio, A minus to HA, will not change if you dilute it. You're not changing the number of A minus there and HA there. You're just changing how much volume they're in. Right? And if you're looking at that and you're saying, well, it has to do with concentration, it's concentration over concentration. If I change the liters, they're going to cancel out. If I go from 50 milliliters to 100 milliliters, you're still got the division of 100 on both the top and bottom, and they cancel out. So keep that in mind. And I think I'm just going to I'm going to stop there. I think that's enough for you. Yeah, that's enough for you to realize what's going on. I just want to, yeah. And then we'll look at the buffer capacity part. But, keep all of this in mind. Try to think about it. Try to process it. What does it really mean? How does it change? Put it in your own words, because you're going to have to, A, be able to describe how to make a buffer given material, and they can choose what to give you. And B, how does it actually work? And if you're not sure, guys, use your textbook. Go in the back, look up buffers, read the introduction part out of the textbook on how does a buffer work. Because that's why, people go, oh, it's so hard, it's so hard. It's just equilibrium. That's all it is. You've got to keep it in mind. Don't hit the panic button. Think, this professor keeps telling me it's only equilibrium. So, well, if it's only equilibrium, what am I disturbing in the system, and how will the system respond? Okay, that's all it is. It's equilibrium. Alrighty. So your homework is, hopefully you've filled in the notes as I go along, and you're going to do the buffer problems and check them on page 4 to 5 in your notes. And you're going to do 2, 3, 4, and 5. Calculate out the starting pH of those buffers. And you should have taken notes all the way through page 6. Although yours might be different. I think I have an old version of my notes here. I picked the wrong one. Alrighty.